welcome to the last but one lecture. So you're almost there. Like Andrew said, today's lecture is about biomineralization, but looking at biomineralization from a material science perspective. And so I have sat through some of the lectures, the previous lectures, and I have heard Anders, author, and many other eminent scientists talk passionately about biomineralization, various aspects of biomineralization, its application as far-reaching as coral preservation and such. Now, I am a mechanical engineer, and I'm assuming many of you are engineers as well. But just to get a general sense, how many of you are environmental engineers? Wow. Okay. Any chemical engineers? Science, from physics, science field? Anyone? Okay. Geologists? Okay, good, excellent. Okay, so I am a mechanical engineer, and of course, we engineers, some of us, we like to build things, create new structures, new materials that can have new applications, can solve real life problems, etc. And so I was very intrigued by structures that can be formed by biomineralization, because you see there are such diverse range of structures possible by applying biomineralization. We see them in the biological world. We see this is by far the most complex structure that you will see, which has been created by biomineralization. It's a entirely calcium carbonate based structure, a coccolith, and you can see there's elaborate carvings and very complex exoskeleton, right? And Nacre, of course, through the lecture, you might have certainly seen the structure of Nacre, the internal structure of Nacre over and over, and you will see some of it today as well. And then there is this sponge, which has got, again, very complex teeth-like structure all over its body, in its exoskeleton. Now, the surprising part is when we engineers apply the principles of mineralization in the lab, this is what we get. We get structures which are called rhombohedrons, okay? And there is absolutely zero control over the morphology of the crystals. And this is calcium carbonate. These are calcite crystals, and we can grow them in the lab. I will discuss how. But importantly, there is very little control over the morphology of the crystal, as opposed to what we saw earlier in case of the biomineralized shells. So the objective of this course then is to discuss about biomineralization and basically talk about how we can create new materials using biomineralization, principles of biomineralization. And the process is a low resource intensive approach, okay? And so if we can utilize the principles of biomineralization, we can maybe design, manufacture materials by at the expense of less resources, with low carbon footprint. And we can sort of see what kind of applications those materials can have. So while I discuss, during this course, as we go along, we will talk about some basics of crystallization, how inorganic crystallization differs from biomineralization, and most importantly, structure-property relationship. Speaking of structure-property relationship, I have a small thought experiment for all of you. So you might have seen these shells, right? Or smaller versions of these shells. Now, these are entirely made of calcium carbonate, okay? So I'm going to pass around these shells, and we have many of these. So please pass them around. So basically, you have to take a look at the shells and tell me what is the obvious property that you observe from the shell? The most obvious, feature that you can think of.
Shape.
Yes. Provided by author, by the way. Provided by me. Okay. By the way. So, what do you think? So, shape. Yeah, that's quite right. Anything else? Have you tried playing around? Of course, not try to break it, but what do you think?
It's kind of solid, but not
Solid? Yes.
that shock resistant.
Right. Okay. What is that? Piece of chalk made of calcium carbonate. Easy to break, right? What about that? So a very important characteristic of the shells is protection. These shells are meant to protect the organism that's inside, right? That creates this exoskeleton around it and sort of a protective cover. And therefore, these shells are extremely tough. You apply the same amount of force that I did to break the piece of chalk. No, you cannot break them easily. And that's how they survive over the years, many years. They actually go through a lot of bashing, impact, hydrodynamic forces, and yet they survive. And they are made of calcium carbonate, which, like you saw, is a brittle material. It's hard, but it's brittle, right? We'll get to those terms, as we go along. But basically, the important observation is that these shells, and for that matter, most biological biomineralized shells are extremely tough, are fracture resistant, are stiff, and have great mechanical properties, right? Now, like I said, this contains calcium carbonate, but this also contains something else. And to show you what it contains is this material here, okay? So the shell is basically a composite. It contains calcium carbonate and this organic, okay? And you can take a look around. It's a very interesting organic you can take out and see for yourself. But the way we prepare this organic, sort of extract this organic, is we can dissolve the calcium carbonate and we can then extract the organic, process it, and then we can make plastic sheets out of it. And that's a very important achievement, because a lot of countries now want to ban single-use plastic commodities, straws, anything plastic which creates pollution, etc. A lot of countries want to replace them with 100% sustainable materials. And the fact that we can, extract a sort of bioplastic from a shell which eventually ends up ends up as seafood waste, is a very important capability. So we can maybe utilize this bioplastic or this polymer that's embedded inside this shell to create, plastic bags or other stuffs, because it's biodegradable, it's environment friendly. Okay, but there is a problem. You see, what I have done here is I have plotted the mechanical properties of some of the conventional materials like metals, polymers, composites, and ceramics are up there. So these are some of the conventional materials which are used in engineering applications. Okay, and I have plotted them across two important parameters: the Young's modulus, which is also called the stiffness of the material, and the tensile strength. Okay, and the reason I have sort of plotted them across these two properties is that they sort of give us a benchmark for the load-bearing capability of these materials. So you see, load-bearing property is a very important property because for a variety of applications, you need the material to sustain load. And what these parameters basically mean, stiffness and tensile strength is basically, we can sort of, I can show you with this experiment. We take this plastic sheet and we initially try to pull at it, and it will initially stretch a bit, but when I release the load, it will go back to its original length. It will recover its original shape, right? So that measure of how much maximum load you can apply to this material, while it can elongate but still can recover its original length, is called the stiffness of the material. Okay, but if I apply more force, if I keep on increasing the force, at some point it will fracture, and the maximum force at which it fractures is this one, tensile strength. So that's the reason we use these two parameters to gauge the load-bearing capability of a material. And that's what I have done. And you see that is right here. So its mechanical property evidently is one. Yes, this plastic that I asked you to take a look. So the mechanical property of this plastic is obviously currently inferior in comparison to even some of the commonplace plastics, right? And like I said before, for many applications, load-bearing capability is important. So if you take the example of an implant, for example, biomedical implant, they're currently made using metals and alloys basically, because their mechanical properties are comparable or a bit higher than that of bone, which is why the metals are preferred for these kind of applications. But chitosan is a biodegradable material. You can improve its mechanical properties, and maybe then it will be useful for such applications, because it's FDA approved as well. The material that you just saw, it's FDA approved. Okay, so maybe Nacre holds the clue to improving the mechanical properties of chitosan, right? So Nacre is a composite, like I said, comprising the polymer chitin and the mineral aragonite. But it's not made by these constituents in a random manner. Like I discussed before, there is a beautiful order in which the Nacre puts together these constituents to create this beautiful composite. Basically, if you make a cross section and you see this section of the shell there is composed of these calcium carbonate tablets. And these tablets are sort of like films. They're about 200, 250 nanometers, super thin tablets sitting in a matrix of organic chitin, right? And this arrangement is called a brick mortar structure because they resemble bricks on a cement wall. And there is some level of complexity in the tablets also. The tablets are not perfectly flat. They have some waviness going on, and we'll talk about that. But for now, you need to appreciate that the super thin shell is composed of, these 200 nanometer thin tablets throughout its matrix. And so now we know a lot about crystallization, because crystallization, we have been doing it for a very long time. The simplest process of crystallization is taking salt water, seawater basically, and leaving it out for the water to evaporate, and then you have salt crystals. That's the simplest way. So we know about crystallization, and it's a science which has lots of applications in biomedical field, pharmaceuticals, etc. So we know from high school chemistry that if we dissolve salt, and in this case calcium salt, there is only so much you can dissolve in water. So if you keep on adding more salt to it, it goes to a point where it cannot accept any additional solute, any additional salt in water. And then for calcium chloride, that's represented by this curve. Okay, so this is what we call a saturation line. Now, how do we get to supersaturation then? So what we do is we heat up the solution, and then add more solute, or add more salt. So if we do that, then we get to this point, for instance, and then we can add additional solute, and then we cool down the solution. Okay, so then we reach this point, which is now supersaturated. So supersaturation is basically the ratio of how much solute is currently there divided by how much should ideally be there, right? So here we have a supersaturation, and at this point, spontaneous nucleation can happen. But sometimes this nucleation has to be induced. So if you have seen, have you seen any YouTube videos of liquid ice by any chance? So if you take DI water without any ions, and you freeze it, you take out very gently and place it on the table, it will not freeze. But if you put a tiny bit of ice crystal into it, or you shake it, it will suddenly crystallize, right? So it requires some trigger for it to crystallize, for this crystallization to happen. And the reason for that is crystallization is a process where it's creating new surface. It's going from liquid, where the molecules are rather randomly, moving around, to achieving a more ordered state, where the molecules and atoms are constrained. So for that, there is some amount of energy involved, and this can be calculated. There is an equation there. Don't stress out too much about the equation, but just the important bit is that this energy required for this process to happen depends on the surface energy of the crystal with respect to the liquid around, and the temperature at which the process is taking place, and most importantly, the supersaturation ratio. This is very important. Okay, so since we have supersaturation at this point, we can create these crystals, and that's what we get. And the reason these shapes evolve when we do perform the inorganic crystallization is that you have calcium ions, you have carbonate ions, they have some relative charges, they have specific sizes, and they like to come together in specific ways within the lattice, depending on the various forces of attraction, etc., involved, and they form these kind of shapes, calcite. And then the next kind of configuration is that of aragonite. So here is basically the calcium ions, and around that is the carbonate ions. And then you have vaterite. And then basically these are the three most sort of well-known forms of calcium carbonate, and therefore they are called polymorphs, and they have sort of increasing energy requirement to crystallize. Okay, so for calcite, you require a little less energy in comparison to aragonite and then for baterite, which is why you have an abundance of calcite, and then aragonite and baterite is sort of rare. Okay, and recently they have started to discover even more polymorphs of calcium carbonate, which depends on how much water is present inside the crystal. But basically, these are predominantly the three shapes that calcium carbonate can take. And once they nucleate into these kind of crystals, it then grows. And then grows in a way that, the ions that come near these crystals, they experience sort of greater attraction force across the kinks in comparison to the surfaces, which is why you get these rhombohedral shapes. Okay, it sort of grows. But I'll tell you, there is a deviation from this, and that's the reason aragonite forms. But anyway, basically, this process is the fundamental pathway by which you can make calcite, aragonite, all these polymorphs of calcium carbonate. In nature, we don't see, those kind of shapes. We see so much control over the geometry of the crystals. The constituents, the tablets are sort of flat and very sort of elongated, and these structures, they have all kinds of very interesting shapes, and they repeat. They are repeatable. Okay, so they repeat across the different domains we see. So in order to demonstrate that point, to basically talk about biomineralization, we'll again do a small thought experiment. There is a kangaroo there. So you know that kangaroos can jump very high, right? So do you think humans can outjump kangaroos? Turns out they can. And the founder of trampoline found no better way to demonstrate the point. So this is what happens in case of biomineralization. The biomineralization process sort of takes place through a bit of a trampoline jump. What happens basically is, if you remember, from ions to nucleation crystals, there is a bit of energy involved. But biological systems don't have, the luxury of reducing the temperature or increasing the pH or doing so many different things. Okay, so they want to sort of store calcium carbonate and then use it on demand wherever they want to create these shells. Okay, so whenever they get calcium ions, they want to sort of store them and then later use them. And that happens through an intermediate product. This one, which has a lower energy. So basically what happens is the ions go to this intermediate phase of lower energy, and that then crystallizes into the final crystal form. And these are the amorphous calcium carbonate. So during the previous lectures, many professors, they talked about ACC's amorphous calcium carbonate. It is this entity right here. Okay, and amorphous calcium carbonate is a very important actor in the process of biomineralization. Okay? And this is what ACC looks like. And you can see that ACC, this is scale bar, is 20 nanometers, so super, super small, about 50 nanometers in size, got these vacuoles inside. And these vacuoles, basically what they call is structural water. So that is water molecule embedded inside this amorphous calcium carbonate particle. And here is a molecular dynamics picture of ACC, and these red ones are calcium carbonate molecules, water molecules around it. And so you can see remnants of ACC in various biomineralized structures. And the simplest one is these mineral tablets. And if you zoom in, you will see that they are composed of these tiny little calcium carbonate particles, aragonite particles. Okay, so that's how you know that it went through amorphous to crystalline transformation. And this is a very sort of a very important finding in the field, because um, we always thought we knew a lot about crystallization, but no, in nature crystallization happens through a amorphous to crystalline transformation, and not through iron to crystallization. Okay, it doesn't go directly from iron to crystallization, but from an amorphous state with these particles, which can be morphed, which can be molded into various shapes on demand, whenever wherever the organism wants, and not just random ions floating in the space and then coming together to form randomly shaped particles. So, bit of a text. I think I talked about them already. Is responsible for the unusual geometry of biomineralized structures, and yes, they contain water molecules, and it basically ranges between 0.4 to 1.6. But most importantly, they form because some scientists have tried to. It's sort of difficult to measure, but they have tried to estimate the surface energy, and they find that the ACC has a lower surface energy than the crystal, which is why the ACCs can form so easily. Okay, so all right. So now, important point is for us engineers, can we synthesize ACCs? Because if we can synthesize ACC, we can then maybe create the biomineralized shells, right? We can mimic biomineralization. Fine. So what we did is we go back to our previous scenario, and then we take this solution, and from we were here, right? We cool it even further. So basically, what we are doing is we are significantly increasing the level of supersaturation. Okay. So when you increase the supersaturation so much, the delta G reduces, and then you have amorphous calcium carbonate particles formed in the solution, and then you can store them. But these particles look like that. They're basically ACC in the form of powders. They're composed of very tiny 50, 30 nanometer calcium carbonate particles. Now, obviously, there is not much control over the shape of these crystals. So we may not be able to do much with these powders as far as engineering structures is concerned. And also, importantly, nature also doesn't have this pathway of freezing solutions or reducing the temperature, etc. What they do is they use some biological macromolecules. They use proteins, amino acids. Okay, why? Because amino acids can be sort of charged. They're charged. You can, these are charged molecules which, depending on pH, can associate, dissociate, and based on that, you can attract calcium ions and bind onto these amino acids. So this is sort of the evolving picture of how the amorphous calcium carbonate evolves in the biological system, and it's kind of encapsulated within a shell, or at least in some ways, the macromolecules mediate the process. They participate in the formation of the amorphous domains. And also, if you do that, you can sort of achieve a local supersaturation, because you can bind calcium ions to these molecules. And when you bind outside, the proportion of calcium ions reduces, whereas inside it increases. So therefore, you are supersaturating the amount of calcium that's inside these blocks. So now there are basically two types of additives that we can use to mimic this process in nature. So one way, of course, that's how people previously did. They extracted amino acids from various organisms and then tried to create the biominerals, and that research was exciting, very interesting. But then we also got interested in utilizing some of the charged polymers that we already know about and utilize them to then sort of mimic the process of biomineralization. And there are two types of these molecules. So we have intra-ACC additives and we have inter-ACC additives. And these sort of molecules work slightly differently, and also the results are a little bit different. But basically, what they do is they all have, amine groups or COOH groups, same here, and these groups like calcium ions, okay, and they attract the calcium ions and can bind onto them. The only difference between the two is that the inter-ACC additives sort of remain inside the ACC particles that you saw before. Okay. On the other hand, the inter-ACC additives are large molecules. So that's polyacrylic acid, right? Polyacrylic acid, and this is aspartic acid. This is a rather small molecule in comparison to this. You see the N here. Okay, so it's a rather large molecule, greater molecular weight, and so this large molecule cannot get inside the ACC. Okay, instead it chooses to stay on the on the rim, and the calcium ions are embedded inside the particles. Okay, and you will see that they sort of result in different kinds of structure property relationships. One example is this one, where what the researchers did is they incorporated aspartic acid. So they utilized aspartic acid that I showed you before to biomineralize. So you see, as you increase the amount of aspartic acid here, you also change the archetypical rhombohedra, right? You do not have the rhombohedra here. So it's sort of more deformed, and the structure is very different than there. Okay, and the important result here is that by incorporating these additives inside the calcite, you can increase its hardness. So hardness means that if you have the table, if I press on it, I cannot make a dent on it. Okay, so this table is hard. It's resisting the force of penetration that I'm applying to the table, right? So basically, on a molecular level, what's happening is that the lattice is trying to resist the force that I'm applying, right, in here. Now, so what's happening here is when you have this is the calcite rhombohedra structure, and when you have these additives sort of incorporated between the lattice, okay, they sit between the lattice, they get inside the lattice, and they constrain the lattice. And when you constrain the lattice, when you apply force, the external force, you cannot deform these lattice planes easily, because there are things sitting between the lattice which restrict further deformation of the lattice, which is why what you observe is that this calcite, you see there is a dent, but the height of the dent is much smaller than here. And this is a sort of single crystal. This is a rhombohedra. And this calcite, you see fracture. So calcite is basically a brittle material. So brittle means it's, if you try to break it, it will break easily. Even if its stiffness is high, it can break easily. It's not fracture resistant. So here you see calcite fractures, not here. Okay. So this is a very interesting sort of structure property relationship that they observed, that by incorporating the intra-ACC additives, you can make the calcite lattice harder. Okay. All right. Now, this is the work that we did. Is we utilized inter-ACC additives. Okay. Now, if you remember, inter-ACC additives are these large molecules, and in this work, what we did is we used polyacrylic acid. So it's this molecule here, and like I said before, polyacrylic acid, owing to its COH minus, likes calcium ions. So what they do in a solution, they will go and bind to the calcium ions. They will try to incorporate as much calcium ions as possible. And they create these kind of vacuoles, okay, sort of vesicles. Okay, so to make you understand what I mean, if you think of soap solution, in soap solution you have these hydrophobic, hydrophilic end, right? And the hydrophilic end are sort of facing water molecules, and the hydrophobic ends face each other, and that creates a vacuole. The same kind of situation here. And within this vacuole, you can incorporate calcium ions. All right. So this is something that people have tried before, and they observed the formation of ACC by this process. Okay. So what we did is we got even more ambitious. We said, what if we utilize the chitosan here? Because chitosan, again, this molecule here, this material here, you see it has got these positively charged amine groups, and we have COH minus here. So maybe they will like to come together, and we will see creation of some new crystals. And that's what we did. So when we incorporated chitosan, this chitosan film into this crystallization solution, what happened is that these calcium polyacrylic acid network sort of started binding onto the calcium to the chitosan surface because of this amine COH interaction. And as they grow, they sort of build layers epitaxially. Okay, so they create layer by layer formations of calcium carbonate, ACC to aragonite transformation. So here we got these kind of crystals. We got films of aragonite in this case, and you can see these films are sort of, they cover a large area of this chitosan film. In fact, I have a film right here, and you can take a look. It looks a bit whitish, and there is some difference in mechanical property, which is pretty obvious. You can see if you compare these two. So that is mineralized, this is not. Okay, so the fact that now we can form films of aragonite is a very important result, because we can, we have gotten a bit closer to creating nacre-like structures, because nacre is composed of films, and here we see that we can also create these calcium carbonate films on chitosan surface. And you see here, these are the nucleation centers, and as the crystal grew, it sort of has these sort of footprints of where it started crystallizing, and this is the same kind of structures you see in nacre also. You see in nacre these kind of films forming, sort of growing inside out, and then meeting the next growth front and stopping there, which is why you get what is called the Voronoi patterns of these crystals, sort of a mosaic of calcium carbonate tablets. All right. So clearly, we sort of got one step closer to biomineralization as opposed to inorganic crystallization, where typically we have, these rhombohedral crystals forming, no control over mineralization. Whereas here we at least have some level of control over the crystal geometry.
How do you stop the formation of these layers? How do you, it runs out of calcium, basically? Or...
Yes, yeah, it runs out of calcium, or you quench it by just taking the chitosan from the solution. But then there is the risk of incomplete mineralization. So you will have spots where there is no calcium carbonate films forming. But there are ways that we sort of try to overcome that. So the key here is polyacrylic acid. So actually, interestingly, this whole approach began by using polyacrylic acid as an inhibitor that cannot allow calcium carbonate mineralization to happen. On the other hand, this is what we got. So it just controls the mineralization process rather than stopping it.